The paper today, which is the effect of raster orientation and notch insertion on fracture toughness of one of the polymers mostly used in additive manufacturing, in using the extrusion method. The paper is elaborated in cooperation with my PhD student, Cosmin-Florin, with my colleague, Galațanu Sergiu. All we are from University Polytechnică Timișoara, from Romania, and Professor Octavian from University of Limoges in France. Okay, sorry. So a short summary. So I will start with an introduction. I will show you some preliminary results. Then I will discuss about the material and methods, the results of the static and dynamic tests that we perform, and finally some conclusions. So the purpose of this work was to evaluate and compare the fracture toughness of polyethylene tetraphthalate glycol, right? Specimens produced by fused deposition modeling under static and dynamic loading. So, taking the idea of the panel discussion on Tuesday, so it is better to be approximately right rather than exactly wrong. So I did this after the test. Actually, I asked ChatGPT which is the values of the fracture toughness of this type of material obtained via FDM. So the answer was quite elaborated, and we will check with our results the correctitude of this result. So they saying that for this type of material, the fracture toughness is between 1 to 3 megapascal square meter, which is typically for polymeric materials, but also it gives some hints, a reference paper that they say that the upper bound of the fracture toughness, which was kind of composite materials PETG with ABS, the upper limit was 3.8 megapascal square meter. So we will compare this with our experimental results. So additive manufacturing for polymers became very used nowadays, and material extrusion is one of the most used technique, additive manufacturing technique to be used in rapid prototyping. There are some, let's say, advantages: shorter production time, it's easy to be customized, reduce the labor cost, it's cheaper to make prototypes, and reduce material waste. If we compare, for example, with what for photopolymerization, the resin that is not photopolymerized, so it's a waste. In the same time, for power bed fusion, also we have the powder that is not used, which is also a kind of waste. Where is used this technique? So more and more, but usually the most industries that are using this are electronics, automotive, in medical, architecture, and now aerospace, actually also in education. I will not stay too much on the methodology, but usually it's a filament which is extruded, then heated through a nozzle. The temperature for plastics are between 200 and 240 degrees Celsius, and this is extruded. The extruded material is deposited on a print bed. So the advantages are accessible technology, wide range of materials, achieving now with big printers large scale printings, and it's a relative fast manufacturing technique. However, there are some disadvantages. The quality of surface is sometimes very poor. There are some structural integrity issues, as in the morning Professor Berto from La Sapienza showed, and for some cases needs additional support structures. So we perform some preliminary tests, tensile tests, considering contour and uncontoured specimens. So we use dog bone specimens, the ISO 527. We did this test on different raster orientations, 0 degrees, 45 degrees, and 90 degrees. And the results are, so the maximum tensile strength was obtained for the 0 degrees orientation. This is around 55 megapascal. And what we also can observe, there are no differences between contour and uncontour, because the contour is aligned also on zero degree. And the tensile strength is decreasing mostly for the 90 degrees, because in this case the raster is perpendicular to the loading, direction. So we also did some shear tests. We follow a standard for thin sheets, because there are no standards for plastic materials and particularly for additive manufactured materials. These are the low displacement curves and some results. Here we got the maximum shear strength at 45 degrees, and somehow it's logically to be this. Lower values for 0, and the lowest value again for 90 degrees or 90 degree orientation. So having this, we manufactured some single edge notch bend specimens. The manufacturing parameters were 80 degrees, the temperature of the bed, 220 degrees, the temperature of the nozzle, an average speed of 45 millimeter per second, the layer thickness 0.15 millimeters. We consider 3 raster orientations, which are 0 degrees, 45, and 90 degrees. And we use 100% infill density. We had some previous tests on PLA, and we got the maximum properties for 100% infill. So we use this. We follow the ASTM D5045 standard for fracture toughness determination of polymeric materials. 3-point bend test, static and dynamic. And the specimens were, the specimen dimensions, 6 millimeter thickness, 12 millimeter width, and a length of 60 millimeters, and a notch. The notch was printed, and then for the contour specimens, we cut the notch with a blade. For uncontoured specimens, we don't do any other cuts. You can see here the cut. You can see also the orientation of the raster. So we perform static test in our lab using a Zwick roll static tensile machine with a load cell of 5 kilonewton. The test speed was 2 millimeter per minute. The tests were performed at room temperature. And for the impact test, we use an instrumented Sharpie with a potential energy of 5 joules, with the impact speed 2.9 meter per second. And also the tests were performed at room temperature. To interpret and to estimate the fracture toughness, we follow this standard. So for the static test, we consider second line with a compliance 5% higher than the linear elastic portion of the curve. For the dynamic test was quite complicated to do this, so we consider the maximum load in this case. Some results and fractured specimens, low displacement curves from contour and uncontoured specimens for the 3 raster orientation. These are from static test, and some results. So the fracture toughness, it's for the contour specimens is between 2.8 to 3.75 megapascal square meter. So the ChatGPT prediction was not so bad. Considering the uncontoured specimens, we get higher values, and the fracture toughness is decreasing with the increasing the raster angle. Here we get 5.8 megapascal square meter and go down to 4 megapascal square meter. For dynamic test, here are some force displacement. So this is an instrumented Sharpie, so we can get the low displacement curve and also the energy versus displacement curve. The fracture toughness in this case, the values are between 2.5 to 3.15 megapascal square meter. Again, is decreasing with increasing the orientation. For the uncontoured specimens here, the maximum values were get for 90 degrees orientation. But what we can see if we plot the dynamic fracture toughness versus the static fracture toughness, what we can see that considering different manufacturing parameters, on the static value, we have a span between 3 and less than 6, 5.88 was megapascal square meters. If we look on dynamic test for the same manufacturing parameters, we have between 2.5 to 3.1 megapascal square meter. This means that the fracture toughness in dynamic case, it's less sensitive to the manufacturing parameters. So we try also to find a correlation between dynamic, because dynamic tests are always more complicated than the static ones. So we try such a correlation to propose. So finally, I will not read all the conclusions, but the takeaway from this is that dynamic fracture toughness is less sensitive to manufacturing parameters, which I think is a very good thing for applications when we have dynamic impact or dynamic loads. So finally, I should thank to the ministry, which support us by a grant, and I would like to thank you for attention. Thank you.